This is Chapter 18, Section 3. We are going to look at the equilibria of acids, bases, and salts. Again, this has a lot of slides that are very wordy. You get down at your own speed, everything that you consider to be important, which is most of this, but I will highlight important things as we go along. So, starting off with this, we're looking at Ka. It's a new term for you. It stands for the acid ionization constant. And this is for specified temperatures and does change with temperature. If you take acetic acid, which is a weak acid, and we're going to be listing throughout this section and the next section all about strong acids, strong bases, weak bases. So if you need to go back to the chapter on acids and bases, refresh your memory on that. Do that ahead of time because I will proceed on with just thinking, hey, you remember what your strong and weak acids are and your strong and weak bases are. So we're going to take acetic acid, which is a weak acid, meaning most of the molecules are going to remain unionized. Only about 5% of these molecules will ionize whenever you mix it, say, with water. And a solution of it, the little bit that does ionize, is going to ionize into the hydronium ion and the acetate ion. So again, most of it remains unionized. If we were to look at the reaction again, you've seen this one before. You have acetic acid and water to give you the hydronium ion and acetate ion. If you were to write out the Ka expression for this, this is what it's going to look like. We do leave water out of the expression. Water is going to remain constant in what it is. It's also considered in its liquid or its normal base form too, so water would not be included. This data, and you don't have to write down this data, it's more important that you understand what it is that you're looking at. Notice that we have different molarities, the percent ionization that you have going on with your acetic acid, and it gives you the Ka, or the acid ionization constant, and it is relatively constant for the set of data that we're looking at here, and this would be for your acetic acid. So now we're going to change it up just a little bit, and we're going to look at what happens if you add a salt to disturb equilibrium. And the salt here that they're going to add is going to be sodium acetate. Notice that the sodium acetate still has that acetate ion in it that can react with the acetate ion from the acetic acid. So there's your equation for acetic acid as it breaks down. Again, only about 5% ionizes. But when you increase it says here the disturbance, meaning you've added your sodium acetate, causes a decrease in the hydronium ion and an increase in the acetic acid because you have effectively increased your acetate ions here by adding the sodium acetate, so that reverse reaction is going to take place. The equilibrium will be reestablished. Notice it will have the same Ka value, the same value of Ka, even though there's a higher concentration of non-ionized acetic acid and a lower concentration of hydronium ions. But the changes in the hydronium ions will affect pH. So we will be introducing along the way changes in pH within this section. So now we're going to look at buffers. Buffers, if you have a buffered solution, believe it or not, when we were looking at acid-base solubility earlier and the equilibria there, some of the things we looked at, which you'll see again today, we were looking at buffered solutions. You just didn't maybe at that time realize that's what they were called, but a buffer solution will resist a change in pH. This is where a buffered solution contains both a weak acid and a salt of a weak acid. We will talk about the reverse of this too, talking about the weak base and a salt of a weak base. But for right now, we're going to look at a weak acid and the salt of a weak acid. So in the buffered solution we just looked at, we had our acetic acid, and then we had sodium acetate, which is the salt of it, and we looked at the acetate ion that the salt could provide to our solution. And A buffered solution can react with either an acid or a base, and with small amounts of acid or bases, the pH will remain nearly constant for part of this solution. It depends on how much you have, and we will look at how long will the pH remain nearly constant with some examples that we'll look at before the section is over. In this picture right here, they are talking about here on the left. The beaker on the left is going to contain your buffered solution. So we do have a buffered solution here on the left. On the right, though, we're going to have a beaker that has mostly water in it with just a little bit of acid. So I'm just going to write water over here right now. It has a little bit of acid, and we have a pH indicator that is put into both of these. And we've already done our lab with the pH indicators. If we go over here to the right side now, if you add 5 milliliters of 0.1 molar hydrochloric acid. Now, hydrochloric acid is a strong acid. That's not a very large concentration of it, though, but 5 milliliters, that's about a teaspoon. If you add 5 milliliters to it, well, for the buffer solution, notice that there's really not a change in the buffer solution. But if you add it to the solution that was mainly water with just a little bit of acid and you add some more acid to it, it will affect the pH, and the pH does lower. So again, if you add a small amount of acid to your acetic acid sodium acetate solution, so that is your weak acid and your salt solution, the acetate ions will react with most of the added hydronium ions to form the non-ionized acetic acid molecules. So the reaction that they're showing you here, this is the reverse reaction of what we were just looking at. So from the salt, you get some extra acetate ions that will react with the hydronium ions to give you your acetic acid. But still, the pH of the solution will remain practically unchanged. Now, if you have a small amount of base being added, so for our bases, we're typically looking at the hydroxide ions of our base. That can remove some of the hydronium ions to form your water. And if we're looking at it right here, again, forming our water, then the acetic acid molecules then ionize and mostly replace your hydronium ions that have been neutralized by the added OH ions. So the hydronium ion concentration and the pH remain practically unchanged in this particular version of the example. So we've been concentrating on our acids. What if we look at our bases? If you have a solution of a weak base containing a salt of a base, it can also behave as a buffered solution. The buffer action has many applications. For instance, human blood is naturally buffered to a pH of around 7.3 to 7.5. Some other examples of the chemistry, if you were going to dye your clothes or even do some fermentation, those are some examples. Just to bring up the whole part about the human blood and its pH, we say water is good for you. You're supposed to drink about 1 gallon a day, but there have been people that have overdosed even on drinking water, and it changes the pH of your system drastically. Now, going back to self-ionization of water, we did see this back when we were talking about hydrogen ion, hydronium ion, and we looked at the equilibrium constant for water. So you have seen this particular equation before. If you have forgotten it, definitely rewrite it in your notes. So we're concentrating right now on Ka. It could be Kb, but Ka, the ionization constant for acids. Here is your setup for the ionization constant for water. So we're going to take this for water. We're going to look at some different salts that react with it in our next slide and look at hydrolysis of salts. Salts are formed during a neutralization reaction between a Bronsted-Lowry acid and a Bronsted-Lowry base. As a refresher, Bronsted-Lowry acids, they are proton donors, and a Bronsted-Lowry base is a proton acceptor. And by proton, we are talking about the hydrogen ion, so H+, the hydrogen ion. Keep that in mind as we go through some of the different examples as we're explaining these things. So when a salt dissolves in water, it's going to produce cations of the base and anions of the acid from which they are actually formed. And I will go through an example of this right after this next part. If the ions are formed from a weak acid or base, they react chemically with the water molecules, and the pH of the solution will have a value other than 7. And I'll also explain to you, well, how does that pH value change. So let's go look at a quick example for this general classification of what they're looking at here, talking about hydrolysis of salts. If I were to look at sodium chloride in water, and that's table salt, the hydrolysis of this right here, you're going to produce the sodium ion and the chloride ion. And talking about how will it change your pH, well, your sodium ion, since this is a salt, you think of, well, where do those ions typically come from? Well, the sodium ion is going to typically come from sodium hydroxide, which is a strong base. Sodium hydroxide is a strong base. Your chloride ion would come from hydrochloric acid, which is considered to be a strong acid. And if I look at the ions they produce, since sodium hydroxide would break down to give you the sodium ion, well, I would expect that the sodium ion to be a weak ion. And since hydrochloric acid is a strong acid, I would expect the chloride ion to also be weak. So the stronger the acid or base is that is being used as part of the salt, the ions of that salt are going to be weaker. They're going to be weaker. In this example, taking the sodium acetate, which has already been mentioned in today's lesson, and I mix it with the water. Again, that's a salt, another salt and water, producing the sodium ion and the acetate ion. Our sodium ion, again, is still coming from the strong base sodium hydroxide, so expect it to be weak. And our acetate ion, though, would come from acetic acid. Acetic acid is a weak acid, so expect the ion from a weak acid to be stronger. Expect it to be stronger. Since it is going to be stronger, if I look at these two right here, both of them are weak and weak, so salt into water, don't expect much change in pH, so not much change going on there. But in the bottom one, because the acetate ion that is being created is considered a stronger ion, expect there to be a change in pH with this bottom one. And when we look at this, we will look at, on this next slide, we're going to look at, well, how could it change your pH? So hydrolysis is the reaction of water and the ions of a dissolved salt. So we just looked at a couple of examples there. If the ions react with water, the process is, or anions, if the anions react with water, the process is called anion hydrolysis and results in a more basic solution. If the cations react, the process is cation hydrolysis and the results in a more acidic solution. So if I were to go back and look at the examples we were just looking at, again, the first one, from a strong acid and a strong base, don't expect much change. But in that second example I gave you, and you had your acetate ion there, so the acetate ion coming from a strong acid, that would be its conjugate base. Expect it, because it is stronger, to create a pH that's considered more basic. So this slide right here goes back to what I was just talking about, and that would have been the second example I looked at of the sodium acetate in water. In the Bronsted-Lowry sense, the anion of your salt, that was that acetate ion we were just looking at. The anion is your conjugate base of the acid from which it was formed. So I've already went through that. The acetate ion coming from typically your weak acid, acetic acid. If the acid is weak, which it was in that example, the conjugate base will be strong enough to remove protons from some of the water molecules. And once equilibrium is reestablished, the net effect of this new anion hydrolysis would be an increase in hydroxide ion concentration of the solution, which means it would be more basic for that example. Here is the equilibrium equation for a typical weak acid in water. So HA is generic. The H is just saying, yes, I'm an acid, and then the letter A is for acid. So we're going to pick a weak acid in water, and remember, they might ionize about 5%. So the general equilibrium equation would look like this for your Ka. Again, this is general. A minus would be the anion that is being produced, and then HA is that anion with H or hydrogen, which is your weak acid. If we were to look at the hydrolysis reaction between water and the anion A minus, here is the dissociation that we're looking at here, and the extent of the hydroxide ion formation and position of equilibrium depends on the strength of your anion. The lower the Ka value of your acid, so the weaker the acid, the stronger its conjugate base will be. So the lower the Ka value of your weaker acid, the stronger its conjugate base will be. We can also say the same things about bases too. So if we took sodium carbonate, which is considered to be strongly basic, the carbonate ions will react as a Bronsted-Lowry base, meaning they are a proton acceptor. So notice that your carbonate ion here has accepted one of the protons from water to create the bicarbonate ion. If I were to look at the actual breakdown of this, you could think of it as sodium carbonate. So there's our salt. Sodium carbonate breaks down into the sodium ion and the carbonate ion. Again, if I think of where the sodium ions normally come from, they come from sodium hydroxide, which is a strong base. So this ion would be considered a weaker acid of it, weaker conjugate acid. And then the carbonate ion would come from carbonic acid, and carbonic acid is a weak acid. In your soft drinks, think of that. It is a weaker acid, so this conjugate base that is produced would be considered a stronger conjugate base than the weak acid it's coming from. So this might help you too in the breakdown as you get down to the aqueous solutions in their ionization state here. So the hydroxide ion concentration will increase until equilibrium is established. In the Bronsted-Lowry sense, the cation of a salt, so we've looked at the anions of the salt, the cation of the salt is the conjugate acid of the base from which it was formed, so it's a proton donor. If the base is weak, the cation is an acid strong enough to donate a proton to a water molecule to form the hydronium ions. Equilibrium is established so that the net effect of the cation hydrolysis is an increase in hydronium ion concentration of the solution. So we're looking at the flip side of what we've done now. So the cation of a salt is its conjugate acid, meaning it's coming from being a proton donor. If the base is weak, the cation is a stronger conjugate acid, and equilibrium will be reestablished to increase the hydronium ion concentration of your solution. And we'll look at an example going this direction. So we're going to take a weak base. They're just using the letter B for a weak base. It could be any weak base. Again, they might only ionize about 5% with water, and that weak base will accept a proton to give you BH+, and then water will, since it's the proton donor here, is creating the hydroxide ion. The Kb, or the base dissociation constant, would look like this in this particular example. I know that this symbol comes up a couple different times in the slide, not really sure why it does. That right there should be OH minus. So again, OH minus right there. Not really sure where the G is coming from. So if we're looking at the hydrolysis reaction of what just happened, now we're looking at the reverse of it, because the cation produced by the dissociation of the weak base B is listed here. So it's the reverse reaction. The extent of the hydronium ion formation and the position of equilibrium depends on the strength of the BH+. So that is going to be the conjugate acid produced from our base. The lower the Kb value, the weaker the base, the stronger its conjugate acid. So again, we've already explained this on the flip side in detail. Now you're just looking at it from a base standpoint. Instead of watching this video right here, I'll basically go over what is in the video. So we're looking at cation hydrolysis. If I were to take ammonium chloride, so this is another salt, it would break into the ammonium ion and the chloride ion. The ammonium ion itself is going to be from ammonia, which is a weak base. So ammonia is a weak base, therefore expect the ammonium ion to be a stronger conjugate acid. It'll be a stronger conjugate acid. The chloride ion, as you've seen earlier, the chloride ion would come from hydrochloric acid, which is considered to be a strong acid, so expect your chloride ion to be a weak conjugate base. This would give us a final solution that has a pH that's going to be lower, so it would be an acidic pH, since this would be our driving factor for the pH. So hydrolysis, it can explain the endpoint of a neutralization reaction that can occur at a pH other than 7. You've already seen these before, but if we added into this, our salts can be placed in 4 different categories, just like when we worked on this back when we were dealing with just acids and bases. You can have a system that's a strong acid and base, strong acid, weak base, weak acid, strong base, or weak acid and base. And we'll look at a couple of neutralization curves for this. Again, you've seen them before, but now we're going to add in that buffer region. So salts of a strong acid and base produce neutral solutions. So neither the cation nor the anion is going to be an aqueous solution, because remember, they ionize completely. Aqueous solutions of salts formed between a weak acid and a strong base are basic, and the anions of the dissolved salt are hydrolyzed by water, and the hydroxide ion concentration increases. That raises your pH. So in this neutralization curve, again, you've seen this before because we were talking about where would an equivalence point occur between those 4 types of systems. So in this example, we're looking at our buffers now. If we had a mixture of the acetic acid, which is our weak acid, and the acetate ion is added, because we'll say that you've had a salt, sodium acetate was added there. If you add sodium hydroxide, so between these two, you're going to have your buffer region. If you add sodium hydroxide, which is a strong base, you can see how this curve actually happens. But when you're first adding your sodium hydroxide, in this buffer region, you're only going to have very small changes in pH. Notice we do reach an equivalent point above 7 because this is a basic solution. And then at some points you will have just your hydroxide ions that are in excess. So now we'll look at the other way. Salts of strong acids and weak bases will produce an acidic solution. The cations that are hydrolyzed in water, again, your hydronium ion concentration increases, which means the pH is lowered. So if you have a salt of a weak acid and weak base that can produce either acidic, neutral, or basic solutions, it depends on the salt being dissolved. The salt that is being dissolved, where do those ions normally originate from? A strong or weak acid or base that's giving you that salt. In this one right here, we're looking at a strong acid and a weak base and the neutralization curve that we've got going on with it. But to start off with, we do have a weak base ammonia that we have right here. It is being buffered with the ammonium ion. It could have been the ammonium chloride that we were looking at earlier. So there is our buffer region there. So as you slowly start to add, they are adding hydrochloric acid, which is a strong acid. Initially, when you're adding your strong acid, it's going to hit that buffer region and it doesn't have a lot of effect on your pH. But you will reach an equivalence point that is below 7, so in the acidic region, before you finally have an excess of hydronium ions. And to finish this up right here, your weak acids, it's giving you the generic equation for a weak acid, strong acid over here. You're looking at your ionization constant for a weak acid, whereas over here, your acid and hydronium ions are going to be equal. You could look at the ionization constant for water. As a reminder, if you're looking at the hydronium ion concentration, they're breaking it down for you, but these were the equations we had. pH is equal to the negative log of the hydronium ion concentration, and the hydronium ion concentration and hydroxide ion concentration, because it's listed right over here, is equal to 1 times 10 to the negative 14th. And that was your ionization constant for water, how we came up with those values.